So in section 14.2, we discussed derivatives and integrals of vector-valued functions for which, well, actually, we're not going to learn any new integration techniques other than the ones we already know from Calc 1 and Calc 2. So all these techniques such as immediate integration, U substitution, trigonometric integration, what else? Trig substitution, partial fraction decomposition, pretty much every single method of integration, it's back. It can potentially be back. All right, a little bit of notation just to put together this calculus with the context of a vector valued function. So, if we have a vector valued function r of t with components f of t in the direction of I, g of t in the direction of j, number one, notice we're only working with one variable, one input, for which we may go from r to R1, from R to R2, or from R to R3, depending on whether we're working on the plane or with vector valued functions on the plane or in space. Our input one single value, our output a 2D vector or a 3D vector. Okay, so the derivative r of t represents the tangent vector to the curve, given our r of t and pointing in the direction of increasing t values. So just think about what we learned back in Calculus 1. You take the derivative. What is that? Well, that's actually the whole motivation to study calculus, right? To find rates of change, to find derivatives, So, and the derivative represented if constant, just the slope of the tangent line to the given curve at a given point. And if it's something more composite, we can use that expression to find those different slopes on the curve. All right. So the result or the meaning of what we're doing shouldn't be so surprising, except that now we're gonna have a curve in space or in the plane, and we're getting the tangent vectors, which, again, there's no rise over run when it comes to vectors, but rather or lines, rather the direction component of the vector that directs the line. All right, so and then we can also define what we call the unit tangent vector, which is, well, that's the tangent vector, which is the derivative divided by its magnitude. That's how we get a unit vector. We're dividing a vector, the components of a vector, by its magnitude. All right, so how about we see this in action with one example? So we're giving r of t equals to 4t minus 1i plus ln of t j plus 4e to the negative 3 tk. So they're asking us to find a few computations. Well, number one, they're asking us to find the derivative. So all we're going to do is find the derivative of each component. The derivative of 4t minus 1 with respect to t. Well, that's simply 4. The derivative of ln of t, that's simply 1 over t. And the derivative of 4e to the negative 3t, well, the derivative of an exponential is itself, so that is e to the negative 3t times by mini chain rule times negative 3. But that negative 3 times the 4 we have in the front of the exponential, that makes it a negative 12, right? So just using your basic differentiation rules. That's it. Again, no new rules, no new methods of differentiation, of integration. It's just how we're going to put it together in the context of vector-valued functions. All right, so for part B, they're asking us to find the unit tangent vector. Well, from the definition box at the top, to get the unit tangent vector, we divide the derivative of a vector valued function by its magnitude. That means we need to get the magnitude of this madness here, all right? Okay, let's get that. So the magnitude of r prime, and again, let me remind that MyMathLab, our textbook, uses just one single bar for magnitude, which to me, that reminds me to absolute value. So, but technically the correct form to represent a magnitude is with a double bar, all right? Just so you don't get confused when you're working on homework or something. Okay, so we need to take the square root of the squares of the components of, in this case, these vector valued functions. So that is 4 squared plus 1 over t squared plus negative 12e to the negative 3t squared. Okay? So that's going to give us what? The square root of 16 plus 1 over t squared plus negative 12 squared, that's positive 144. E to the power of another power, multiply the powers, that's going to give us a negative 6t. Okay? And that's our magnitude. I know what you might be thinking. Should we simplify this guy? No, you don't need to simplify this. I mean, it's an exponential base. E, a constant, a denominator, a polynomial denominator. I mean, you could multiply or get like a least common denominator, but that's not really going to help that much, you know? So you can just leave it like this. That's fine. Now, I believe we're ready to get part B of the problem. Get the unit tangent vector, which, first of all, by definition, that's the derivative that we got in part A divided by its magnitude. That is the derivative of, the magnitude of the derivative of the vector valued function. So, what we got for part A, the first result, that is 4 1 over t negative 12 e to the negative 3t divided by what we got for this radical. Square root of 16 plus 1 over t squared plus 144 e to the negative 6t. Right? And well, I know what you might be thinking. Should we distribute that humongous radical over every single term? No, no need. If it's something this big, something this crazy, just leave it like this. In the end, well, we may or may not need to evaluate at one value. So then, those computations, just do them when you evaluate at a number at a value of t. All right. So that's going to give us all the unit vectors that are tangent. Hey, what happened here? That are tangent to the curve, right? Okay. So for part C, they're asking us to evaluate the second derivative at 1. So what we got for part A, let's find the derivative of that. That's all we're going to do. Now, here is the thing. What we got for the first derivative, I'm talking about this term right here. So, make 1 over t equals to t minus 1. So you can easily differentiate this using the general power rule, because we can't differentiate like this when the variable is like that in the denominator, right? Okay. Second derivative. Well, number one, we need to find r of t, or rather r double prime of t. That's the second derivative. That's going to give us a 0. That's the derivative of t to the negative 1. That's negative t to the negative 2. And the derivative, that is negative 3 times negative 12. That's positive 36 e to the negative 3t. So now we may divide, or rather we may evaluate this at 1. All right, but you might want to rewrite this with positive exponents. Negative 1 over t squared, 36 e to the negative 3t. That's our r double prime. Okay? Now we may evaluate this. R double prime at 1, that's 0, negative 1 over 1 squared, comma, 36 e to the negative 3 times 1. And I know we're going to get weird numbers. That's going to be 0, negative 1, and 36 e to the negative 3. I know we're no longer working with vectors such as 1, -3, 5, or the like. Now we're getting into more elaborate vector valued functions for which we will bring up every single function you know today. Tricks, exponentials, logarithms, inverse tricks, etc. All right. Okay, how about you guys try letter D? See what you get. Okay, letter D. They're asking us to find the dot product between the derivative and the second derivative. So the first derivative, which I checked it with this check right here, that is 4 1 over t negative 12 e to the negative 3t, dotted with, I'm not gonna have enough space in here. Never mind, I'm gonna make it smaller. Dotted with 0, -1, 36 e to the negative 3t. Well, dot product between two vectors, x components with x components, 4 times 0, that's simply 0. 1 over t times -1, that's -1 over t. And which one? Oh yeah, t squared, right? This one. I was looking at the result. Yeah, thank you. That's 1 over t squared, 1 over t cubed, right? So 1 over, and not a vector, right? So that's 0 minus 1 over t cubed. Minus times a positive, big number, is that 432? E to the negative 3t. You might want to get rid of this 0, that's fine, you don't need it. And again, notice in this case, we are not getting another vector, we're getting a scalar. That's the result of getting, performing a dot product, a scalar, not another vector. All right. So in this section, we are just discussing the tools of how we're going to perform this operation. But in the next exercise, we're going to introduce a little bit of what this means. And well, this shouldn't be surprising from what you learned back in Calc 1 and what you may or may not have reviewed in Calculus 2, which you apply this a lot in your physics course as well. In the same way, when you're giving a function, f of x, take the derivative, f prime of x, and then take the second derivative, f of x. So the easy, or the most straightforward application you got for this derivative, well, that means, number one, the position of a particle traveling along some curve described by f of x. Then the first derivative represented the velocity. What about the second derivative? Acceleration, right? So in a similar way, what about r of t? That's the position vector. That's where a particle is on the curve. Could be a line, could be a spiral, whatever that is. Then go from the r of t to r prime of t. That's going to give us the velocity vector, whose direction is going to go in the direction of increasing values of t. Of course, you can define it so it goes backwards. That's where you would need to reparameterize the function in a way, all right? Change signs, or maybe change the order of the parameterization. There's a bunch of ways to get that. And r double prime, that's our acceleration. So in this case, we would also denote it as a v of t. It's not the same as the regular v vector we worked on during the first chapter. This v now literally means velocity. R means position vector. And then we can go from there to a of t. So you don't need to put the prime symbol, because I guess the letters we're using are pretty much very self-explanatory, right? So velocity and acceleration. All right. So for the next exercise, what do we need? Okay, I think I'm gonna need the calculator for this. Yeah. So we're gonna get to our calculators in parametric mode to have a look at this exercise part. Should be exercise 1 anyway, or 2. All right, so we're given the path of an object given by this vector valued function. It's a polynomial function where t is given in between -2 and +2. All right, so they're asking us to sketch the path and be sure to indicate the orientation. That's very, very important because just a graph like what you did from the first time you plotted, you graph functions by plotting points through most of your calculus, it's not going to be enough. We need to indicate the orientation of the curve. I'll show you how. Okay, so let's go to the graphing calculator. Okay, make sure it's in parametric. Okay, it's already in parametric mode from last time, and I'm just going to clear whatever we have, and I'm going to type the new function. So that is t squared plus t, and for the second component t squared minus t. All right, and then graph. Most likely you may not get the whole graph. You may get something like this. Also, when you graph a vector valued function, make sure not to blink because you may miss the direction in which the graph is being plotted. I'll show you how to slow it down in a second. In the meantime, well, it seems like I'm not getting the entire graph what I want. So I'm going to go to Window, and I'm going to make my t-min to be, what was that? It's a -2, right? -2, and I'm going to go to, not to 2 pi in this case, to 2, because we're not working with circular functions this time. Okay, graph. Well, it looks like it's going in this direction like this, right? If you want to slow it down, well, go to Window again and make your t-step a little smaller than what you have. Typically, you get by default a 0.1 or a 1. Well, here we have a 0.01, which is still a little quick for our function. So I'm going to make this 0.001, even smaller. What is this? So these are the steps. That is the number of order pairs our graphing calculator is plotting to give us the entire graph. And the smaller the steps, the more points it's going to plot for us, and therefore that's going to go in slower motion. So we're ready? Clear? Oh, not clear. Graph. Now you will be able to see this in slow motion because now the direction matters. This is to indicate, well, let me go back to the notes. So this is going to give us function right here. But we need to indicate the direction with arrows like this. All right? Not the other way around. All right, so that's part A. All right, that's part A. Okay. Part B, find the intercepts algebraically. I mean, clearly you can see that from the graph. You can see that the intercepts are, number 1, the origin, 0, 2, and 2, 0. Well, we need to get this algebraically. Well, again, how do we get intercepts? How do we get the x-intercept of a regular function, even if it's not parametric? How do we get that? X-intercept. What was that? What do we set equal? Y. In this case, it's the y component of the vector valued function. All right? So let's set x of t equals to 0, and let's set y of t equal to 0 and solve the equations. That is, t squared plus t, set it equal to 0, and we can easily solve this polynomial equation by factoring. We can factor out t times t plus 1, set that equal to 0, and using the zero product property, either t equals to 0 or t equals to 1. I mean, t minus 1 equal to 0. That means t equals to 0. It's still t equals to 0. And here, t equals to 1. All right? All right, now let's find the x-intercept. That is by setting the y equals to 0. Well, the y equation, which is t squared minus t, set it equal to 0. Again, solve this polynomial equation by factoring t times t minus 1 this time. And again, zero product property, t equals to 0 or t minus 1 equals to 0, which means t equals to, actually this was plus and this is negative 1. I don't know what happened here. All right, yeah, got it. Okay, so notice the t equals to 0 result is repeated. So when we work with this, you just work with it only once. Now, here is the thing. They're asking us to find the intercepts. These are not intercepts. These are the values of t. That is the times t where a particle going along this curve, those are the times at which it crosses the x-axis, the y-axis, well, and in this case, the origin, which is technically both x-intercept and y-intercept. That's why we're getting t equals to 0 for both. All right? Well, so what are we going to do with this, with these values? Well, let's substitute in the original vector valued function r of negative 1, that is, evaluate this at the original function t squared plus t, that is negative 1 squared plus negative 1 comma negative 1 squared minus negative 1. Careful here. So what's that going to give us? Well, number 1, negative 1 squared, that becomes positive 1 plus negative 1. They technically cancel out. That's going to give us 0. And negative 1 squared, that's also positive 1, minus a minus becomes a plus, which is 1 plus 1 equals to 2. But again, these are vectors. These are not order pairs. They're asking us to find the intercepts algebraically. Again, intercepts are order pairs or order triples, depending if we're working in space or in the plane. But these are vectors. However, recall that we can simply turn a vector into an order pair because these points on the line, on the curve, on the parametric curve, on the vector valued functions are the terminal points of vectors in standard position. All right, so 0, 2. Isn't that one of the intercepts that we got visually? Right? Let's get the other two. R of 0. That is 0 squared plus 0 comma 0 squared minus 0. That's simply the vector 0, 0, which is the point P 0, 0. All right? Which is the origin, just the same way we got it graphically. All right? And last but not least, we will repeat the process for t equals to 1. That is, r of 1 equals to 1 squared plus 1, 1 squared minus 1. That is 1 plus 1, which equals to 2, and 1 minus 1, which is 0. That is the point 2, comma 0, which is this point right there. So we just verified everything here algebraically. Right? Now, if you want to verify this using your graphing calculator, of course, you might want to go to your graphing calculator and click on second table to get a table of values here. So notice how you get the point 0, 2 for t equals to negative 1. You get 0, 0 for t equals to 0. And for positive 1, you get 2, comma 0. You get the three intercepts. Well, they're actually pretty much neighbors, right? So because they're nice integers of values of t. Okay. Now, very oftentimes we would need to find So we would be given a vector valued function. And again, vector valued functions have one input, or an input that is one element, or rather one integer, and the output, which is a vector in either two components or two dimensions or three components. However, oftentimes we may get a mixture of values of t versus order pairs, so we need to know how to get back and forth between one system of the other. So the question here is, what is the value of time at the point 2, 6? Well, I mean, you can easily go and check this out on the graphing calculator. So you look for the point 2, 6, and you're going to get the value of t for -2. But what if you were given a curve in space? Your graphing calculator doesn't graph functions in space, and well, on a quiz, or well, rather on an exam or something, you're not going to have access to GeoGebra to graph that, so, and create a table of values. So we need to know how to do this algebraically. Okay, so let's see how that goes. So we're given a vector valued function which it's the same as this representation in parametric form, where we have an x equation and a y equation. The x equation is the x component of the vector valued function, while the y equation is going to be given by the y component of the vector valued function. So here we will set the x component of the parametric equation. The x equation equals to the x coordinate, and the y equation equal to the y coordinate. All right, and that's how we're going to get the time at which a particle is at the point 2, 6. All right. Because again, typically it's the reverse. Oh, find the position after 5 seconds, after 9 seconds. And all we do is simply substitute the vector valued function and rather evaluate it at the given value of t. Now we're going to go backward. We're going to do the reverse. Okay, so let's set t squared plus t equals the x coordinate that equals to 2. And on the other hand, t squared minus t equals to the y coordinate, which is 6. Well, in this case, we have a couple of quadratic equations. Let's have everything on one side. That is, move the 2 to the left-hand side, and move the 6 to the left-hand side. All right. So, and in this case, we need to solve two quadratic equations. Keep it simple. I know there's a bunch of methods to solve quadratics by using the quadratic formula. You don't need it, to be honest. Completing the square, you don't need it either. It's going to be overkill to use the completing the square. Every time you have a quadratic equation, try factoring, and hopefully that doesn't take you more than 10 seconds. If it's already taking you a good minute, just use the quadratic formula. All right, so here we can easily factor these two trinomials because number one, or potentially because number one, the coefficient on the square term is 1, so we can potentially use the double bubble method. That is, we would find factors of -2 that add up to 1, and those numbers are +2 and -1. That means either t plus 2 equals to 0 or t minus 1 equal to 0. Okay? And that means t equals to -2 or t equals to 1. How about the second quadratic equation? Well, let's do the same. Let's solve that equation by factoring. That is, using the double bubble method again. T factors of -6 that add up to -1. What do we have? -3 and +2. That means either t minus 3 or equals to 0 or t plus 2 equals to 0, which means t equals to 3 or t equals to -2. But hold on, we got a bunch of results, a lot of potential options. No, it's not like we have options. So we need to go with the one that repeats. That is, the one common to both, which in this case, let me highlight them, that is t equals to -2. All right? Which actually checks with what we did by looking at the table in our graphing calculator. All right? So when you're asked when is the particle at a given point, well, you will need to set the the two components of the vector valued function equal the x-coordinate and the y-coordinate we want to find that time for, right? And just go with the one that goes common to both, because very often times you will get something like a quadratic like this for which, or a cubic for which you may get more than one solution. So just go with the one that's common to both. And again, go to the graphing calculator, that's a -2. So if you keep making a larger table of values, that's not going to give us another value of t at which the particle is at the point 2, 6. Okay? All right. Let me go back to the note. And again. Letter D, find the velocity and acceleration vectors when t equals to 2 and sketch them on the same graph at the appropriate position and label them. So again, velocity, and although velocity and acceleration, it's something we're going to get into more in depth in the next section. I think this is a good point to introduce what these derivatives and second derivatives of vector valued functions really mean. All right, so let's find the velocity vector. We no longer need this prime in this case. We can simply say v, that is, okay, v of t, which is really, okay, if you want, r prime, just so you can connect ideas here. Okay, so the derivative of t squared plus t, that is 2t plus 1. But we need to evaluate the velocity when t equals to 2. That is 2 times 2 plus 1. Oh no, that's 2 times 2 plus 1 and 2t minus 1. Forgot to differentiate the second component. So that is 2 times 2 minus 1, which equals 4 plus 1 equals to 5. 4 minus 1, that equals to 3. Next up, okay, well, we need the acceleration vector. That is, let's label it a of t equals to r, in this case r double prime. That's the second derivative. In the same way as for scalar functions, that's the same with vector valued functions. All right, that is, okay, the derivative of 2t plus 1, that equals to 2. The derivative of 2t minus 1, that's another 2. And well, if we evaluate the acceleration at 2, well, notice in this case we don't have any variable t, so we can substitute that 2. In fact, the acceleration is constant. It's going to be the same vector for every single point. All right, so just keep it 2, 2. So now we may go back to the top of the page to plot these two vectors. So I'm going to go to to the point where t equals to 2. Okay, let me go back to the graphing calculator. For t equals to 2, we have the point 6, 2. Okay. However, you might want to get this r of 2. Get it algebraically. That's 2 squared plus 2, 2 squared minus 2. That's going to give us 4 plus 2 equals to 6. And 4 minus 2 equals to 2. So which means the point 6, 2. Okay, so let me go to the point 6, 2. That is 6, 2. Let me get rid of this part right here to make it look better, more accurate. And at the point 6, 2, I will plot the vectors that I just found. The velocity vector, I'm going to use green for the velocity vector. I'm not going to have enough grid. That means 1, 2, 3, 4, 5, and 3, roughly here. Right? So that's going to be our tangent vector here. And that's the velocity vector v, 5, 3. And the acceleration vector at this same point, 2, 6, that's going to give us the vector 2, 2. That means 1, 2, 1, 2. That is somewhere here. And I'm going to get this vector, right? So that's vector valued functions in action, not just the vector part, but also put together with some algebraic situations such as finding intercepts, such as finding the values of t at which a particle is at a given point, okay? And again, for a very simple polynomial vector valued function, it works just factoring the polynomial, but you may get trigonometric, you may get something like exponentials, logarithms, that may give rise to solving exponential and logarithmic functions or other kinds of radical functions right here. All right? Okay, let's see what's next. So, notice how the differentiation rules for vector valued functions are pretty much the same. I mean, like the general power rule, differentiating a sine, cosine, logarithm, exponential, that's not going to change. Inverse trig functions, so all those the differentiation rules you have learned throughout Calc 1 and 2. Just change the variable x for a variable t and give them the vector valued function context. That's all that we're going to do. However, we may get to see 3 different product rules. So, because we may get number 1, the product between a scalar function and a vector valued function. So the product rule works the same, in general when you have fg prime, that means f prime g plus g prime f. The derivative of the first factor times the second plus the derivative of the second factor times the first one without doing anything. So it's not going to be an exception when we have these combinations of products, because when it comes to scalars and products, more new combinations will come into play here. All right, so here we have the first combination, a scalar times a vector. So here, that is the derivative of the vector valued function times the original scalar function plus the derivative of the scalar function times the vector valued function. All right? Now, what about number 2, the dot product? So the derivative of the dot product. So that is the dot product between the derivative of v times u plus the derivative of u times v. And again, this is another another product rule, but in this case, one that involves a dot product. And the same for the cross product rule. So that is the cross product between the first vector valued function and the derivative of the second factor plus the cross product between the derivative of the first vector valued function and the second one. So it just goes with the same cross product. And I mean, we're gonna be using some of this in the later sections, actually, when we get to the differential geometry section, which wraps up this chapter, by the way. But let's do something like case number 1. So in this case, they're asking us to differentiate the product between a scalar and a vector. How can you tell it's a scalar times a vector? Well, the notation gives it away. There's ln of t, which just looks like a scalar, and this u with bold case, or if it's written by hand with an arrow at the top, that indicates it would be a vector valued function. But hold on, this is a vector in a special way, a vector composite function. All right. So, because it's a composite function, somehow we will combine this product rule with, with the chain rule somehow. Okay, let's see. So, the derivative of the first factor times the second without differentiating. That is simply ln, the derivative of ln of t, which is 1 over t, times, well, I'm not going to use this dot instead because I don't want to make this look like a dot product, because there's no dot product between a scalar and a vector. The dot product is again between two vectors. That times u of t squared plus the derivative of this factor. Well, notice this is just like a generalized function that it's composite at t squared. We could have a vector in the plane or in space containing trig or what else, exponentials evaluated at t squared. But in this case, it's just any generic vector. So that is u prime of t squared, and then by chain rule multiply by the derivative of what you have inside of the parentheses, which is 2t. That times ln of t. And well, here I would just like to clean up parentheses. There's really not much to do. So that is 1 over t u of t squared plus 2t ln of t u of, or rather u prime of t squared. But again, when it comes to finding unit normal vectors, other unit tangent vectors, we're going to perform the other rules right here. This is just to give you the heads up of what's coming up in the next part of the next few sections. Okay. What's next? The next topic in this section, it's about differentiability and smoothness. And well, again, this is going to take us back to Calculus 1 when you were differentiating functions. However, functions may not be differentiable at all points in their domains, because what if a function, well, let me go back to Calc 1 today, in Calc 1. What if a function has a vertical asymptote? Well, it's not even in the domain for that value of x if we think about it. So it's not in the domain. What else? What if a function like the absolute value function that has a cusp? So it's not differentiable at the point where the cusp is, because, well, I think a graph would be better. For instance, when you have, this is a nice and smooth curve so far. However, we get to this point right here where we have the sharp corner there, where we have the cusp. So you can compute the derivative at every single point. That's going to give us what? The slope of the tangent line at that given point. And then another one here. And then another one here where it's 0, for instance. But what about at the cusp? So you guys agree that there's infinitely many slopes here. So if you put like a line, it could be this one right here. It could be a horizontal one. It could be another one here. So there's infinitely many slopes at that point. So that's why we have the slope undefined at this sharp corner. All right. How are we going to take this to the next to vector valued functions? Well, so in this case, a vector valued function will be considered smooth on an open interval I that we will define if f and g and h indicate f and g if we're working in R2, and f, g, and h if we're working in R3 are continuous on the interval I n wherever the derivative of the vector valued function it's not equal to the 0 vector. This should be the 0 vector. In other words, this is what we're going to do. We're going to take the derivative of the vector valued function, set those components equal to 0, and those values of t are going to be the values where the function is not going to be smooth. All right? Okay, so again, let's have a look at one example. Given the vector valued function r of t, 2t cubed minus 7 halves t squared minus 5t, comma 1/3 t cubed minus 1/4 t. Sketch the curve indicating the orientation and determine the intervals and the points where the vector valued function is smooth. All right? Okay. So let's have a look at the graph for this. Again, this is a vector valued function that can be rewritten as a set of parametric equations. And that's so we can graph it on our graphing calculator. Right? So all this is going to be our x equation, or x of t, and all that, it's our y of t. Okay? So, let me go to the graphing calculator. Let me start with a fresh set of equations. Get rid of them. So that's going to be 2t cubed minus 7/2 t squared minus 5t. And for the second component, that is 1/3 t cubed minus 1/4 t. And you're going to get a really weird graph. Yep. Okay. Do I have the signs correct? Yes, I do. Okay. So this is going to go, well, actually, I'm not even, oh, yes, it's giving me the entire graph. Well, let me maybe add a larger interval for t, maybe -2 to 5, right, to get a better picture. And it's a little slow because, again, it's still using the t step from the previous exercise when actually that's going to help us a lot to keep looking at the direction. So number one, let's graph. Let's try our best to plot. Okay, it's about 1 point something, and then 1, 2, 3, 4, 5, almost 6. Okay, 1 point something, 6, about 6. Okay, so here. Okay, so I'm gonna get like a straight. It looks a lot like a straight line, and then this curve right here. All right. Now, from this graph, you can see the sharp corner. That is where the derivative of the vector valued function is not defined. All right, well, so how about we do the calculus for this to find the values of t at which the function is not differentiable, or rather, it's not smooth. It's differentiable but not smooth, rather. That's because we may not find the tangent vectors at those points. Okay, so let's find r of t. R prime, rather. So that is 6t squared minus 2 times 7/2 minus 7t minus 5, comma 1/3 times 3, that's just 1, t squared minus 1/4. All right? So what do? We set these two components equal to 0, solve for t. All right? So that is 6t squared minus 7t minus 5, set it equal to 0, and t squared minus 1/4, set it equal to 0. Okay. So we need to solve these two quadratic equations. All right? So to factor this trinomial here where the leading coefficient is not equal to 1, I'm gonna use a factoring technique that you may or may not have seen before. It's called the slip and slide method. How does that work? Well, I'm going to come up with a different equation. Here I'm going to multiply 6 times -5. That's going to give me a -30. So here then, that's going to be a -7t, and the 6 in the coefficient will disappear. All right? It's going to go away. That equals to 0. And now we will factor this trinomial using the double bubble method. It's going to work. It's guaranteed to work unless we are getting a prime trinomial, which could be the case. So factors of negative 30 that add up to negative 7, what are those? 3 negative 10. So that is t minus 10 and t plus 3. That equals to 0. But hold on. I'm not going to use the zero product property just yet. What did we do to come up with this new equation? Notice how we multiplied by 6. So we did something. Now we need to undo what we did. How do we undo? Well, if we multiplied by 6, divide by 6. Divide by 6. Okay? Now, if it goes evenly, if you get a nice integer, well, then go for it. All right. However, in this case, just reduce the fractions. That is t minus what is that? 5/3 and 3/6. That's t plus a half. Well, we're still getting fractions. So this is what we do. I'm going to move this denominator to multiply with t. These two multiply with t. That's going to give us the equation 3t minus 5 times 2t plus 1 equals to 0. And then you should be able to use the zero product property. That is 3t minus 5 equals to 0. 2t plus 1 equals to 0. That means t equals to 5/3 and t equals to negative 1/2. So that's only the result for the first equation, for the first derivative of the first component equal to 0. Let's do the same with the second one. Well, here for this baby quadratic equation, you have a couple of options. Use the square root property, that is, move the the negative 1/4 to the right, and then take the square root on both sides. You can do factoring here as well. That is t minus 1/2 and t plus 1/2. Set that equal to 0. That means t equals to 1/2 and t equals to negative 1/2. All right? What are we going to do again? We're going to take only the value of t that is common to both. That is negative 1/2. All right? This is the 1. Okay? This is the 1. Okay. Now we have a result. So r of t is smooth in the interval negative infinity to negative 1/2 union negative 1/2 infinity. All right, so that's where the vector valued function is. It's smooth. Okay, or you could say it's not smooth at t equals to 1/2. But depending on what you're being asked, maybe you're being asked for this result as a vector value, as an interval notation, or just finding the value. All right, where it's not smooth. Now, to get the point where r of t is not smooth, evaluate the vector valued function at negative 1/2. But look at this ugly looking vector valued function. That's going to give us some trouble. How about we use our graphing calculator, look at the table, or evaluate. However, I'm going to change the settings for the table. I'm going to go second table set, and I'm going to have the independent variable not to generate automatic values. I'm going to make it ask a value. So when we do the ask, go second table, everything is gone. Now you input your favorite value of t to evaluate the vector valued function, in this case negative 1/2. Okay, and click enter, and that's going to give us this weird order pair. All right. Alternatively, just do it by hand on your graphing calculator. Use the frac command to get the point. All right. Okay, so